Welcome to this video on the topic of vectors. In this lesson, we're going to learn about a vector operation known as the dot product. Then we're going to explore its application. The dot product describes the likeness of the direction of two vectors. Suppose we have vectors A and B, and we wanted to apply the dot product to it. Then what we'd find is we'd have an expression that looks like this. Expanding this out, what we might find is that our expression on the right of this equation would look like as follows. So the dot can go between the brackets of the vectors in component form. Now, evaluating this, the method we employ is we multiply the members of each vector with its corresponding one. So it would be A1 multiplied by B1 plus A2 multiplied by B2. And then we just sum all the products together to get a final result. So as you can see, we multiply the corresponding members of the vectors that have been dot producted together, A1, B1, A2, B2, then we sum them all. So the final result, we get a scalar quantity, so a singular number. Now, let's have a look at why this is an important operation. As mentioned, the dot product describes the likeness of the direction of two vectors. So having said that, what we're going to find is that we're going to get three different situations that we encounter. The first one being that we encounter a situation where we have a similar direction of vectors. Consider we have one vector that points like this, and we have another vector that points sort of like that. This is vector A, this is vector B. Notice that they're mostly pointing in a rightwardly direction. In such an instance, what we find is that the dot product of these vectors is going to yield a value that is greater than 0. So this is a similar direction. They don't have to point in the exact same direction, they're just pointing in a similar direction. Now the next situation that we might encounter is, I'm going to do it over here, I'm going to say it's a not similar. In such an instance, what we discover is that the vectors might point, one might go that way and the other one might go down like that. In such an instance, we could say that this is vector A and this is vector B. And when we take the dot product of these two vectors here, we discovered that the outcome is less than 0. Now the final situation that we encounter when we're doing the dot product is when they are perpendicular. So such a situation could look like a vector pointing like this and another one going up like that. And we discovered that they intersect at a 90-degree angle. In such an instance, what we discover is that when we take the dot product of both vectors, vectors A and B, we get a value of 0 coming out of it. So, as you can imagine, the dot product is a fantastic way to determine whether two vectors are perpendicular or not. Or we can discover whether they're mostly pointing in a similar direction or mostly opposite. But this one in the middle here is typically what we use the dot product for, to check whether they're perpendicular. Okay, now that we've seen the definition of the dot product, as well as why we think it's useful, let's have a look at some examples. Example A. Consider we have vectors A and B defined over here. What we want to do is we want to determine whether vectors A and B are perpendicular or not. Now, given the situation we saw up here, if two vectors are perpendicular, then the dot product will be 0. What we can do is we can build a statement and then check whether it's true or not. If the dot product of vectors A and B is equal to 0, then vector A is perpendicular to vector B. So what we need to do is check whether the left-hand side of this equation is equal to the right-hand side. Setting this out, I'll say that the left-hand side equals A dot B. Next, I'll sub in the values for A and B. A is 6i, 3j, and B in this instance is going to be -4 and 1. Working our way down, we'll evaluate this expression here. Notice one's in unit vector form, the other one's in its component form. There's no need to convert them into the same form here because we can just go straight into the dot product, which would be 6 multiplied by -4 plus 3 multiplied by 1. Saving a bit of space. 6 4s are 24, but it's negative 24 plus 3 is negative 21. So our left-hand side here is negative 21, which is not equal to the right-hand side because remember, the right-hand side we were expecting it to be 0. So the left-hand side does not equal the right-hand side. And because this statement over here is not true, we therefore know that vectors A and B are not perpendicular. So this is our result here. So to summarize, we wanted to determine whether vectors A and B are perpendicular or not. The way in which we check for this is we say, well, if they're perpendicular, then A dot B will give us 0. So the dot product of the two vectors will give us 0. We therefore check to see whether this expression does evaluate to 0, so the expression on the left, in which case it doesn't, so therefore we conclude that the vectors are not perpendicular. Alright, let's have a look at a different scenario. For what values of M is A perpendicular to C? Whereas if we observe the values of our vectors here, A is 6i plus 3j, and C is -2m, where m is clearly an unknown. What we're going to do is something very similar to the previous example. We're going to build our statement, and we'll say, suppose vector A is perpendicular to vector C, then the dot product of A and C has to be 0. Building from this, we know that this statement over here is definitely true because we're forcing it to be true. Vector A dot C has to be equal to 0 because we're forcing it to be perpendicular. From there we sub in our values. Again, we're mixing different forms for vectors. It doesn't matter. We can simply evaluate the dot product as the form it's in. 6 by -2 plus 3 by m. No need for parentheses here. All of this is still equal to 0. Working our way down. 6 2s are 12, but it's negative. Plus the 3m. I rearrange, and then I solve for m. In which case I discover that m is equal to 4. Now the question asked, well, what value of m is A perpendicular to C? Well, A is perpendicular to C when m equals 4. And there's our solution. So to summarize what we did here, we were not checking if something's perpendicular, but we were forcing something to be perpendicular. The way in which we do this is, if two vectors are perpendicular, their dot product must be equal to 0. So we build an equation where the dot product of two vectors is equal to 0. Because one vector has an unknown in it, we can simply solve for the unknown for when it makes this statement true. In this case, m is 4, so when m is 4, these two vectors are perpendicular. So to summarize, in this lesson we learnt about the dot product of two vectors. We discovered that the dot products can be evaluated by simply multiplying the corresponding members of each vector together and then summing the products, or summing all the products together, so we get a scalar value. From there, we learned the meaning of the dot product, or at least one that we can derive from it. If we have perpendicular vectors, the dot product is 0. If the vectors point in a similar direction, the output is greater than 0. However, if the vectors point in a dissimilar direction, then the output is less than 0. And from there we just did two examples. The first example showcasing how to check whether two vectors are perpendicular or not, and the second one showcasing how we can force two vectors to be perpendicular if there's an unknown in one of the vectors.